Hey there, geometry students. This is Mrs. Brunk. Welcome back to class. We are going to be taking a look more at these three-dimensional figures that we've just gotten done studying about volume. And that meant like the capacity to fill up one of these three-dimensional figures. But in this module, we're going to look at how much material would it actually take to create this outer shell, this container that we want to fill up with the volume we just talked about, right? So we want to look at how we can make a three-dimensional solid or surface and how much material it takes to make the outer shell. So lesson 19.1 is about cross-sections and solids of rotation. And our learning goal is we're going to be able to describe 3D shapes formed by a net and describe a cross-section. So I just use the word net, and what a net is basically a diagram of the surface of a three-dimensional figure that can be folded to form the three-dimensional figure. So it's kind of like if you see a cardboard box all taken apart and laid out, and you want to turn it back into a box and how you kind of fold it together. So the net would be like what it looks like when it's all flattened out so that it's almost essentially two-dimensional, right? And then, how we can kind of connect it back together to make a three-dimensional shape that we can actually put stuff in. To identify a three-dimensional figure from a net, look at the number of faces and the shape of each face. So, we've looked at both prisms / cylinders. Those were the figures with two like faces, like a top and a bottom, and then they had like lateral surfaces like the sides, right? And you may remember that like a prism could have like a shape of the bases be like triangles or pentagons or whatever. They would be called like pentagonal prisms, triangular prisms, square prisms, or boxes. They could also have circles as top and bottom, and then they would be called cylinders. So the thing that was very definitive about them is they had a top and a bottom that were parallel, and then the lateral surface or the sides were all some sort of quadrilateral. Usually rectangles, the ones we looked at were mostly like right prisms. So they were like a bunch of rectangles on the sides that kind of closed in the sides and connected the top to the bottom. And even if you took the lateral surface, the sides, in other words, off a cylinder and flattened it out, kind of like a soup can label. If you took a label off a can, it would be a big rectangle, right? So if you see something that has two bases on it, it's going to be some sort of prism or cylinder. And you remember the pyramids? They had like whatever, they have one base, right? Maybe it was a triangle or a square or a pentagon or whatever as the base, and then the sides all kind of converge, or all the points on the base converge to a vertex point. So if you think about looking at the sides of those shapes, like maybe one of these right here, like this, see how the sides were triangles of some sort, usually isosceles, unless they were kind of slanted pyramids. Whereas we had, these rectangular faces, like see, these are rectangles around the edges around here on a prism. So that helps us to identify the category that they are, whether they're one base or two base, and then we can name it by whatever the shape of the base is. So, for instance, this first one is a rectangular prism, and the reason why I know that is the base down here is a rectangle, and there's a parallel base on the top that's just like it, right? So it's got two bases. They're both rectangles, and so then it's a prism. And then if I looked at the net, like if I kind of tore it apart, that's a typical box. One way it could look, and this is not the only way, but one way it could look is that we've got our top here. This is that top piece, and this is the bottom piece. And then these are the sides. This whole thing makes up the sides, right? These would kind of wrap around, and that would form our sides. Now, as far as this question here, and you can see they have it kind of described the faces as a pair of congruent rectangles. The three pair that would be congruent would be like this one right here. Oops, let's see. if I can do a little better job of highlighting that in. So we've got like this one here and this one here. Those are congruent, right? And then we have a pair here and then a pair here. So like you think about if you were able to take this and wrap this around, this edge right here, right there, would align here, and then this line right here aligns there. So like it would, you wrap it around, you fold those tops down. These are the parts that would connect, right there. So then we've got one other pair of congruent rectangles, and that would be this pair right here. So this pair right here, and these are going to connect those other spots. Like this spot right here would connect right here with that. This part right here would connect with that part right there. This part with this part, this part with this part, right? So then you can kind of imagine it folding it up and making it back into the box that it started with. So as far as the faces, that's where we see 4 of these faces on the sides and 2 pair are congruent, and then we have the top and the bottom that are also congruent. Now this next one is a triangular prism, and it's a triangular prism because, and it's actually kind of a deceiving because it's laying on one of its lateral faces, but the bases are actually these triangles, and it's one's on the front edge where we're looking right at it, and the other one is behind back here on the back, right? If we stood it up, it might look like this. It might look something like that. And then, so you can kind of see the top and the bottom are the triangles. And when we lay it out, you can see that the top, or maybe this is the bottom, and this is the bottom, again, are, if you were to kind of fold them along these edges here, right? And then you just kind of wrapped this whole surface around this is like the sides right here, right? And they would kind of just line up right along. These would line up here, right? But then you just kind of wrap it around and like fold the triangle towards each other to make a top and a bottom, and then just wrap the sides around. So it's got a pair of congruent triangles, and that's got 3 rectangles that kind of wrap around the sides. Now this next one hopefully is very clearly a pyramid. You see it's got, if you look at this net, you've just got one base here, right? And then you've got basically all of these sides that are going to converge to a single point. Like all of these points where I'm putting these, if we were to fold along these edges right here, right? All those points would meet right straight above the center of that base, and they would make this shape right over here, which is a rectangular pyramid. And again, the base is a rectangle, right? So this is a rectangle, and the faces are all triangles. And actually 2 of the pair are congruent. Like these 2 triangles over here are congruent, like the one over here and the one over here, those are congruent. And then you've got your ones over here. These are going to be congruent because, again, they're on the 2 opposite sides of a rectangle, which are congruent. And then the cylinder, I don't see a picture of a cone, but we'll have one in a second. So the cylinder is, you've got your top and your bottom, of course. So you've got your circles on the bottom, your circle on the top. And then you see those here, right? Just kind of folded down. And then you've got that like soup can label or whatever, you know, like the lateral surface right around here, right? This stuff around here, that's going to just get folded down and make into one big rectangle right here. So this is like what you see around here, right? All that stuff right there, that's what you see, but it's just laid out, okay? You can kind of imagine dissecting a cylinder. That's what it would look like. Now, one of our main goals is to just kind of get comfortable with what it takes to actually make these 3D figures, because then we're going to study surface area. So in other words, how much material it takes to make the surface. So we want to just get practice at knowing, you know, like how many faces or what the shape actually looks like, you know, to make it up. So then we'll find out later on what the area of all that is. All right, now, just being able to look at a net that we would actually make out of maybe, say, cardboard or plastic or whatever, and then create those 3D shapes out of. And I always have models of these in my classroom. They're really cool because they'll have like the little plastic nets inside. I can pull them out and lay them out flat, and you can see how they would fit into the solid, clear 3D container and just kind of, create that surface. So basically what we have to do is look at these nets and then first of all see how many bases are there. Are there one or two? So you can see there's one, 2 here. And they're 5-sided figures, right? There's 1, 2, 3, 4, 5. So that is pentagon. So we would say this is a pentagonal prism, because the prism is the one with the 2 bases, the top and the bottom. So basically like that. I know we might be more specific, like if you looked at the base and the sides in the base were all congruent, then we might call it a regular. Which means the base is a regular pentagon, meaning all the sides are equal in the base there. And then you might even call it right, because see the whole lateral surface is a rectangle. So that means if we were to make this into a 3D figure, the 2 bases would be right over top of each other. So the sides would form a right angle with the base. And so we could also throw in that it was right, R-I-G-H-T, right? It's making a right angle with the base. So that's another way that sometimes we'll classify. These are all the lateral surfaces here. There's these 4 lateral faces, all rectangles. I'm not doing so great. Okay, we'll just trace them this way, like that. The next one has just one base, right? Just one. And so we know it's some sort of pyramid, and what kind of pyramid we can tell is by looking at the base and what shape it is. So it's a square. Well, it looks like a square, so we'll call it a square. So it's a not rectangular. We'd say a square. If it looked like the sides were not all the same, we might call it rectangular, but it's a square pyramid. And again, because we can tell that the triangles they look like they're all isosceles. It kind of looks like the points will meet right directly over the center. So they're not going to be one of those slanted pyramids. So we might say it's also a right pyramid. A right square pyramid would also be. So again, may or may not put that in there. We don't really have perfect evidence to say that, but we might call it right as well. With this one, again, we see all these triangles here, but it's kind of like, they were all these triangles over on the sides here were just sort of peeled off the base. This is the base there. And it's like they all kind of were just peeled off along these dotted lines and just laid out flat. So we know it's a pyramid. The base is that triangle, so we don't know what kind of triangle it is. So we just, to be more general, we could just say triangular. Triangular pyramid. Okay, so we're just looking for clues based on what the shape of the sides are, which you can see in any pyramid, the sides are going to be some sort of triangle. In any prism, it's going to be some sort of 4-sided figure. Usually it's a rectangle, but it could also be parallelograms if it's one of those slanted prisms. And D is probably really obvious that it's a cone. Okay, so if you can kind of imagine like this edge getting bent and wrapping around like this around. So like this side over here would wrap around that side, here would wrap around that side, and then this would be like where the vertex is. So that's the vertex, and that would create into a cone. Now, one of the other things that we look at in when we study 3D shapes is what would, if we just took a slice out of the 3D figure, like, and depending on the angle, it'll look different. But if I just took a slice out of it, what would that shape of that little 2-dimensional slice be? And again, it depends on the angle that you go into the figure at, and whether you're kind of cutting through, like for instance, this first one, see this plane here goes in and like a little slice out of space, right? And we just cut out, and you can see that that little shape in there is a circle. It actually almost looks like it's an oval, but remember when we draw cylinders, we make the bases look like they're almost like ellipses or ovals or whatever, just to give it that depth. It's hard to, if you draw like a straight up circle, it's going to be hard to show that it's three-dimensional. So anyway, so all we do is when we want to figure out a cross section, we really just look at what shape, if we look inside, when that hits inside the figure, what shape is made. So we're really just looking at this right here. Okay, and the shape would be a circle. It's actually going to be congruent to the base. Okay, and that's because it looks like, it's crossing in there. It's going parallel to the two bases. That plane is slicing kind of going at the same slant as both the top and the bottom. So parallel through there. Now, if instead, let's say we took and we drew like a plane like this. Oops, I can't make it sideways, I guess. If we went through like this, maybe. Like this. Then you'd see like it would hit up here on the cylinder and then maybe down here on the cylinder. And then it might make an ellipse. It might stretch it to the side. So, it just depends on the angle that plane is coming in there. But this particular one, and you usually can just look at the drawing, is pretty good. You can tell what that shape is by just looking at where it crosses. Now, this is a cone, and it's a cone that the plane is going in there and hitting right. It's kind of going in right at the vertex and looks like it's splitting right straight through the base like this, right? Like that. And so the shape they're really looking for when they're asking for the cross section, you can see it's highlighted in here in the dotted lines. It's basically like they're cutting straight through and getting a little triangle out of there. So that's a triangle. Okay, some sort. And it's probably isosceles. If we wanted to be very specific, we'd say it's an isosceles because these edges right here are going to be the same length, right? So we'd say it's an isosceles triangle. Again, just to, it just depends on how specific the question wants you to be on whether you're going to say just plain triangle or whether you're going to be real specific and say, oh, nope, that is an isosceles triangle because you got two equal sides. And then if you had a cylinder and then you just slice straight through the top and the bottom, now you're going to get, see this little piece right there? It's going to like go down one of the edges on the side and it's going to create a rectangle right there, right? So that'll be, your cross section will be a rectangle. So really a lot of these problems, it's just a matter of just looking at the drawing, and they usually do a pretty good job of showing what that slice out of there is. It's sometimes hard with three-dimensional figures and you're drawing them on a two-dimensional, say, computer screen or in a book. But now the final thing we're going to look at is we're going to see if we can figure out what sort of three-dimensional figure is formed by rotating the following shapes. So if you took a triangle like this right triangle here, and you rotated the triangle along one of its legs, okay, because this is a right triangle, so that's one of the legs. So if you can kind of imagine kind of taking this side right here, this side right here, right, and kind of just swinging it around, and it would end up the exact same spot on the other side, right? So it would end up right over here, exact same distance away, right? And then it would keep going around until it came back around. If you rotate it all the way around, what shape would form? Well, what that's going to do then is create all the way around that exact same shape, and you can see that it's a cone. And specifically, it's a right cone, because see that 90-degree angle right there? That means that that vertex is going to be directly above the center of the base, so it's going to be a right cone instead of like an oblique or slanted cone. Same thing with the next one. Okay, we've got this rectangle, but this time we're going to be rotating this piece right here around. We have like an axis. We have an axis right here that we've made one of the sides of the rectangle be the axis, and we're just going to spin the figure around it. So we're going to spin basically C will move. B's going to stay right where it's at because it's already on the axis, right? A's not going to move, but D's going to move. And so D's going to swoop around here like this, the exact same distance on the side. C's going to swoop around here like this. And they're going to continue around and come back till they come back to the start, right? And then you can see that what's happening is it's turning into a cone. I'm sorry, not a cone, but a cylinder. Sorry. C-Y-L-I-N-D-E-R. And specifically, it's going to be a right cylinder. And again, it's because, see, this is basically at 90 degrees there. We've got that rectangle. And so rotating around, it's going to rotate around and create a base that's directly right above the other one. And so it's going to be a right cylinder. Now, with something like this at C, some of these points, like, so we have this as an axis. I mean, you probably can tell what this one is too. I mean, it might actually just look like it's going to be a circle when you get done. But actually, if you think about, like, say, points here, when it rotates around, it's going to go in close, right? The further out they go and they rotate around, they're going to be out further on the other side. Put a point here and rotate around. And again, you're going to continue on the other side that we can't see, right? But you're going to keep going around and then back around on the other side. And all of a sudden, here, now we go around, right? And we've created a sphere, right? And we've got, oops, I did not do a very good job of drawing that. Oh, we've created a sphere. And that furthest point out here, right here, when it swings around there, it creates that great circle in the center, which is that largest circle in there, and that's where we get the radius from. So that's just a little look at some aspects of these 3D figures that are like two-dimensional slices, or like the two-dimensional piece of material that we need to create them, or what's called the net. So then we'll move on in future lessons and we'll take a look at how we can actually calculate how much material we would take to make some of these containers or solids or whatever. So that does it for today's lesson. Thanks for coming to class.